Talk to me. So, how is Schrodinger's cat explaining what is happening and taking place in the double slit experiment?
It explains how the electrons were in a superposition, and then the detector was placed, and the superposition collapsed.
Make anything you want to add?
Pretty good.
You can't, it's like, when you have the
And the cat
detector,
was in
it's
the
like,
box, he didn't know what it was wrong until he opened it, and that's how the detector, he knew exactly what was happening, because the detector made it switch out to two bands.
Beautiful job. Really good job.
He said, "You saved
So,
the house."
just let's take them together to draw the relationship between the two. So you did the science part perfect. Like I would be ecstatic if I read that on a quiz. So here's the thing, in the double slit experiment, we get from electrons, whenever we send them through the two slits, we get an interference pattern, which is a property of the wave. Since we get that interference pattern, that's the property of the wave, we look and say the electrons were waves. How is this happening? That's where the whole conclusion comes with the thought experiment. You put the cat in the box, the cat is alive, the cat is dead, it's dead alive, it's alive dead. It's in a state of superposition. It exists in all possibilities until you open the box. Once the box is open, at that point, then the superposition state collapses, and we know what state the cat is in. Just like with the detector, we knew which slit the electron went through. Okay? Pretty good job. What?
RC. Superposition. Did you say superposition?
Superposition. Okay? So, here's what we're going to look at doing today. I got a couple things to finish up with this, and then we're going to start into the quantum numbers. With the quantum numbers, they become like little puzzles, honestly. Typically, everybody really enjoys them because it's like electron configurations. It's literally the same thing, but we're combining them together. It's just in a different representation. Here's the thing. If you cannot do an electron configuration, you should be coming and seeing me during lunch. We got to get you where you can do an electron configuration. Quantum numbers are very similar, just slightly different. But it's just like with the electron configurations. You figure the puzzle out, and once you have the puzzle figured out, then you are set.
Are we trying to send it?
You will. So, double slit experiment is freaky and weird, right? Electrons even get more freaky and weird than that. Not only do they exist in nature, bonded to themselves, but there's something else that takes place. Inside of an orbital, how many electrons can be in there?
what? Is the orbital is the,
It's all you, bro.
Is it 10?
give me a second.
2, good job. You can only have 2 electrons in the same orbital. That's it. You can't have more than 2. So when we look at this, what are electrons?
Make the thing charge subatomic particles.
Thank you. Negatively charged subatomic. Everybody's on the edge. They're like, oh God, this is supposed to be really confusing. So negatively charged subatomic particles. What do things that are like charges do? If you looked at me, you would say that I am an introvert or extrovert. If you looked at my wife Mary, is she an introvert or extrovert? We're attracted to each other. Okay? Opposites attract. What do like charges do?
Like move away from each other.
they move away or repel. Okay, so we call it repulsion, or they're going to repel. So shouldn't electrons repel from each other? So whenever we did those orbitals in orbital notation, we did stuff like this. We did an up arrow and a down arrow. There's a reason for the up arrow and the down arrow. I'm going to go ahead and preference the up arrow and the down arrow. That is to represent the fourth and final quantum number. We call it the spin quantum number. So what happens are electrons actually spin. So as they're spinning, they spin in opposite directions, and I'll go more detail about it later on, but they do this to overcome that natural repulsion. Here's the weird thing, because the quantum realm is even weirder than what you think. Why is your foot and your butt on my desk? Standing means standing, sir.
Is that you, Biggie?
So here's what happens. We can take these two electrons out of that orbit. We separate them. As we separate them, we take one electron in one location and the other electron to the other location. And we teach them, like, you know, teenagers that are in trouble.
Wait, so they're both electrons?
Yeah, both arrows are electrons.
Okay, why do we only put the up arrows in there?
Because it's not full charge.
Up arrow, down arrow.
He just draws his arrows.
But why do you put, like, in the orbital notation, why do we only put the up arrows for, like, when we're finishing out the...
Oh,
So
why are we
at the
at the
beginning?
end? No, at the end, whenever we're like, if we were only on.
So like germanium, where you asked me on germanium, it
Yeah, and
was
there, you
form
want to
A.
put like 3 of them or something?
So why with germanium did I do this?
Yeah.
How far in into the P block is germanium?
2.
2. So
There's
that
2
tells you
arrows.
2 electrons.
Yeah.
So
But
the
why-
rule
Okay.
goes, it's Hund's rule. So Hund's rule states that each orbital of the same energy level will receive 1 electron before it receives a second.
Oh.
So, like if I had a third electron, it's going to go here in this empty spot first. And then we go back through and fill with the down arrows. True. I write a lot. Okay, so
I just not about why we do like
Oh, I get
the
it.
like 2, the 1 for the S block and then the 2 because how many arrows there are. The 3 for the P block
It
because
doubles.
we need to have 6 spaces and then 5. It's not about that.
It's just, there's,
I didn't put-
it's like, there's two.
Johnny, wash your hand on it.
why you ain't on the desk?
I'm
Standing means standing, not leaning.
So there's like 2 electrons, say like, that one's P block, right? Say, there's like 3, what's the 3 lines?
Orbitals.
There's 3 orbitals, so for each orbital, there's 2 electrons for it. So there's 6 total blocks in total.
Oh,
That's just how.
say that again. There's 3 orbitals and there's what?
Like, there's 6 top block, well,
6 columns.
6 columns total in that block. So it's like, for each one, there's 2 electrons, so you like count it. So you go 1, 2, 3, 4, 5, 6. That's just how I
What does blood yellow mean?
Care. Here's the thing, this is gonna make a lot more sense tomorrow when we go through the quantum numbers, because we're gonna break down the periodic table. That's my goal tomorrow, to break that down into quantum numbers. And when we break that down, it typically clicks and everyone's like, ah. I'll go ahead and tell you. I've taught it quantum numbers first, then electron configurations, taught electron configurations and quantum numbers first. It works better to do it how I did it. You're gonna get mad at me when I do the quantum numbers. You're like, man, if you would told us this, it would've been so much better. No, it wouldn't if you're gonna think it would've, because I presented that information first. If I presented this information first, you have nothing to go with, and it just sucks.
Boys over there.
So these 2 electrons, we separate them out. We take one to one, place one to the other. Here's the interesting thing. What do you think will happen if I take the 1 electron and I change its spin? What happens to the other electron?
It changes its.
So it changes its spin. But that's like a teenager in trouble, doesn't have a cell phone, can't get on Facebook, can't even, it's got no Snapchat, nothing. It can't communicate to that electron. How in the world does it do that?
I got a clue, bro.
Cool thing of it is what Kinley says. If I change the spin of one, it changes the spin of the other. It doesn't matter. We can separate the two electrons out. Matter of fact, they did this. They did this experiment, and it was done in California. I want to say Berkeley. There was one university, and there was another one that was close by that they used for the housing for the second electron. They would change the spin of one electron, the other one would change. They changed it again. They changed it again. They changed it again. And at the moment they were changing it at one place, the other place would change with it, saying they're connected. So the quantum world is not just strange because we have particles acting like waves, but it also gets weird because we have something when it comes to our electrons called quantum entanglement. So with quantum entanglement, what this is that two subatomic particles like electrons are connected together. So they're connected together in this sense. You change the spin of one electron, it affects the spin on the other. This is the part that gets so weird. Even if they're separated, they're still connected. We can't separate the connection.
So it's kind of like a string. It's,
Which is where, since you went there, because I think you're thinking on the right track.
it's like the string that's connected to the other electron, no matter how far you take it apart, they're still connected.
Which opened up physicists into trying to come up with,
That,
no, this opened the door. Okay, I thought you were thinking of string theory.
no, I just thought string.
Because you said string, it made me think of string theory. Because the idea of it is, if you don't know what string theory is, physicists are actually trying to come up with a theory that intertwines and connects everything in the universe back together. Because everything's
I'm just gonna go
connected
home and
somehow.
watch a bunch of like YouTube videos on this, just.
So it's pretty good. I mean, you'd be like, oh my gosh. So, yeah. One good career, quantum physics, man.
And I bet you quantum jazz is like impossible to learn.
It's really hard.
Yeah.
So the quantum entanglement is there, because here's the thing that's happening with the quantum entanglement. I have to get you to have an understanding of what we're looking at. When we're looking at the model of the atom, electrons are located in orbitals. Now, we've used this term, but I'm not really sure you're very familiar with the term. We look at orbitals. What these orbitals are probability areas of where the electrons are located. Why are we saying probability? The reason we're saying probability is because Heisenberg's uncertainty principle. We do not have 100% certainty of where the electron is located. We're not sure. So what we're having to do is to wait and see and do the calculations to figure out this is where more than likely the electron is. And this is what changes the whole thing. I know you've been in science classes before, and even in here, I still use it as a representation. Everybody gets caught up with the Bohr's model.
Wow.
We look at you, we show a positive center. We can look at you, tell you how many protons are in there. We look at you and say, we got the first energy level, and here's this electron. This actually is not correct. Bohr's model is not right. Bless you. Why is the Bohr model not right? Is the electron in a fixed area?
No,
No,
just in that area.
it's in a probability area. It's in orbitals. These orbitals have actual shapes to them. So it's like the first energy level. In the first energy level, you only have one subshell, or one S. So if you really want to see what it's like, first energy level is like this. It's like a big sphere. Now once you start getting in the second, third, and fourth energy levels, things get weird and different. The reason they get weird and different is S, P, D, and F all have certain shapes to them. S, P, D, and F will have, S is like spheres, P's are like peanuts, D and F are, they're just freaky and weird, and I don't even want to try to explain it. I'll just show you a picture of it tomorrow, okay? Just take my word for it. So what happens here is the electron's in this area. We don't know where, we just know more than likely it's somewhere in here. And this is where we get what is called the electron cloud. Anybody in here heard of anybody talk about the electron cloud? Wonderful. The electron cloud is the area where the electron is at, because the electron never stays fixed. The electron is always moving. It's never in a fixed location. Perfect example is the lab we did. Do electrons stay where they're supposed to stay at? No. When you took the stick, you stuck it in the fire, it went from the ground state to the excited state. The excited state is an energy level where that electron's not supposed to be. So what's the electron do? Returns back to the ground state where it's supposed to be. And it gives off energy in the form of photons, and those photons come off, we can process them with color, yada yada. All that is true.
You're just yapping.
This is what's taking place. What's happening in here, you have these orbitals, areas where these electrons are located at. So everything that we're going to look at, we're trying to find out where they're setting at. So to do this, there's two ways we do this. The first one, we do electron configurations. The second one we do, we look at the quantum numbers. Quantum numbers, there are 4 of them. Typically I'll go through, I've decided I'm no longer going to list them out because we're literally going to list them out and talk about each one of them. So the quantum numbers that we're going to look at is the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. We're going to go through each one of these individually. First one is what we call principal quantum number. You're familiar with it because the principal quantum number, read everything. Bye. Have a great day. Bye-bye. Like she enjoyed being in here.
She got nervous. You don't like it.
That was the quickest activity ever.
She heard all this stuff I was talking about. Principal quantum number, abbreviated with the letter N. You look at the principal quantum number, it has a possible range. So the range for the principal quantum number. N will be 1 through 7,
N's the
and it must be a whole number.
N's the energy level.
Yes. So from this, it shows and tells us something. What it shows is it will show us the energy level. But it doesn't just show us something, it also tells us something. It tells us the row on the periodic table. This may not make sense to you right at this very moment, but it will when we start applying it. Bells are fixed, so I got like 3 minutes. I know you probably have a little bit of questions on this because it's like one of those things I'm introducing you into something and you're not familiar with it. So let's go to the second one. Tomorrow this will make a lot more sense to you. Second one is the angular momentum quantum number. The angular momentum quantum number is abbreviated with a lowercase cursive l. Now, the angular momentum quantum number has a range. The range it can have is from 0 to n minus 1. Since n, the principal quantum number, is a whole number and we can only go from 0 to n minus 1, this must also be a whole number. The angular momentum quantum number will show the shape of the subshell. Telling you the shape of the subshell might sound confusing to you, but it's like, imagine that the shell is the energy level. It's a big ball, and inside of it is different pieces. Remind me tomorrow whenever you guys come in here that I need to give you the tail on an angular momentum quantum number. We will pick up here and talk on quantum numbers. So I want to pick up there today and see if I can get us to where we can actually like do something with them before we get interrupted. So we're probably going to get interrupted today.
Love that idea. There's one right there before.
So looking at this, we went through the first two, principal quantum number and the angular momentum quantum number. We went through this, and I want to make sure you guys get an idea for this, because I've had issues in the past with kids whenever I've talked about this, they get lost if I would ask a question about what a certain quantum number was telling us or what it was showing us. They would get confused on the difference, and they would mix it up. So here's the way to tell the difference. The key is in the word tell and where it comes from. Tell associates with table, so TT. Tell refers to the periodic table. Show refers to the actual atom itself. So, there you have it. Alright? Principal quantum number shows us their energy level, tells us the row on the periodic table. You guys are familiar with this without knowing you're familiar with this. Whenever we was doing SPD and F block and we was doing the orbitals, we looked at this and we talked about that the N was equal to the rho for S and P. D block, N was equal to the rho minus 1. F block, N was equal to the rho minus 2. That still applies here. Angular momentum quantum number, that refers and tells us the block on the periodic table, and it shows us the shape of the subshell. There are set values for it. So for S, L is 0. For P, L is 1. For D, L is 2. For F, L is 3. And it goes vice versa. So if I give you the angular momentum quantum number, and it's the angular momentum quantum number of 2, that means that the block is D block. You got me? Now, let's go to the third quantum number. Our third quantum number is the magnetic quantum number.
What's the,
This is where I have an abbreviation of a small l sub lowercase cursive l. Oh my God.
Is it beside each other, or is like the L lower?
It's lower. Like a subscript. So the magnetic quantum number has a range that can exist from negative L to positive L. It also has to be a whole number.
there's 4 of them?
So then what the magnetic quantum number is going to show us.
Just fell into the office.
This one shows the orientation of the orbital.
What's the orientation?
So it's like the three-dimensional. So X, Y, and Z. It's, if you look at it mathematically, it's very complex how to break it down on like just using X, Y, and Z once you get into D and F. There's mathematical representation to it that's very complex, but kids, you know it. So what we actually do is we actually just use numbers. So you're gonna see in a second. So like, how many orbitals is there in a P subshell? When you did orbital notations, how many dashes did you put?
3.
So there's 3 orbitals. What is the orientation of those? Whenever you look at it, if we're doing P block, L is 1. Since L is 1, M sub L is from negative L to positive L, so that's negative 1, 0, 1. Those orientations, the first one's negative 1, second one's 0, last one's 1. What this would tell us is our column on the periodic table. So kind of like back to what I was just explaining. So let's take like 4D for example. So I have a 4D subshell. So there's 5 orbitals in the 4D subshell. This is the breakdown of what everything is. The 4, that's N, which is the energy level. Then we have the D, which is the subshell. And we use L to get that. And since it's a D subshell, that means L has to be 2. Since L is 2, that means there are a set possible range for M sub L. So if you look at M sub L, the magnetic quantum number, it goes from negative L to positive L, but it has to be whole numbers. So -2, -1, 0, 1, 2. So this first orbital is -2. This next one's -1. Middle one's 0. One's 1, and that's 2. What we keep doing with each one of these, we keep narrowing it down to something. Narrow it down farther and farther. So then we would have in these orbitals we have arrows which represent electrons. So we care about the location of the electron. Everywhere I can narrow it down to so far, the principal quantum number, I can say the 4th energy level, angular momentum quantum number can be 2, so I know I'm in the 4th energy level, in the D subshell, and then the magnetic quantum number, I can tell you -2, which means that we are in this orbital here, so I've narrowed it down that far into this orbital. But there's one last thing we can do to narrow it down even farther. And that is, we can look at the fixed electrons. So this electron, for example, here, has 4 quantum numbers to it. So if I looked at this electron, I didn't do this in first period, but it'd be good to do it here. So if I looked at N, what's N? Well, N is the energy level. Energy level I'm at is 4. The angular momentum quantum number, L, I'm in a D subshell, so L is 2. And then I have M sub L. M sub L is the orientation, and the orientation of this orbital is -2. And then the last one, which I'm going to define here in a moment, is the spin quantum number. The spin quantum number is narrowed down behind a +1/2 or a -1/2. How's the arrow pointing? If it's up, it's +1/2. Down, -1/2. So in this case, +1/2.
Mr. Hall, is that an MF?
Yeah, I was gonna ask you something.
Yes.
Is that plus just a half or 1.5? It's
+1/2.
Okay.
I couldn't think you said he picked that.
So the fourth and final of our quantum numbers is the spin
What?
quantum number. Spin quantum number is abbreviated with M sub S. The range is between two options, two choices. You have +1/2 or -1/2. What this does is it will show spin of the electron.
What's it called again? Spin.
So then the last one is the tell. What this tells us is the element. from the periodic table. Now, big thing with this is why we even talk about the spin of the electrons and why it matters. You have to have an understanding behind that the spin of those electrons are super important, because what are electrons? This is a question. I'm waiting for your response, by the way. Very good. I'm very proud of you all. They're negatively charged subatomic particles. Since they are negatively charged subatomic particles, negative charges, they're like charges. What do like charges want to do?
They move away from each other.
Move away from each other. What we actually call this is repulsion.
Right.
So they want to repel. Okay? Think of it, it's like you're sitting next to somebody that's got some really bad BO. You definitely want to repel and get away from that. You are in massive trouble, my good sir. You done messed up. So there's a natural repulsion force with the electrons. So how is it possible for two electrons to stay in an orbital together? They spin in opposite direction. So one spinning clockwise, one spins counterclockwise. So as they're spinning in opposite directions, if you take something that has an electrical charge and you spin it, it does something interesting.
Yes, you shut her out.
It actually creates a magnetic force. So if you take something electrical and you spin it, this is what they're doing with like electromagnets. This is how it's possible. So as we spin them, a magnetic attractive force comes into play. So the spin of the electrons is there so that there's a magnetic attractive force that attracts them together to negate the natural repulsion force. So the electrons can stay in there together. If we did not have the spin of the electron...
Pardon the interruption, but I do need to remind you that American Fidelity is here today and they'll be here tomorrow. Every employee does have to go see them while they're here, and we've got several employees that have not signed up yet. So please make sure you get that done as soon as possible. Thank you.
What's your question?
Right, oh, that's the one you said, mechanical force is what it was.
Magnetic attractive. Yeah.
So what would make the EMS thing a negative 1/2?
Plus 1/2 and negative 1/2.
Yeah, what would
It's
make
the
it a
up or
negative?
down arrow.
So it's negative 1/2 if the arrow points down. So like in this one up here, I circled the up arrow, so it's plus 1/2. But if I circle the down arrow, it'd be negative 1/2.
How do you know which one do we circle?
I will tell you,
Oh, okay.
or you'll use the periodic table, which is where we're getting ready to go. We're getting ready to break the periodic table down. Okay? So the important thing of it is I need you to understand why the spin of the electron is there. What would happen if the spin of the electron wasn't there? These electrons would repel.
And they wouldn't exist in the same space.
So then we would have problems. We wouldn't be able to sustain and have what we have today. Now, I have a gift. All right.
Oh my gosh!
What I'm giving you is a periodic table. As somebody said, this is like your 7th one. Well, if you include quizzes, you're
Okay, but that's not the point.
So what we got to do is we're going to go through this thing.
Okay, you can now. How many colors we need?
Burp.
Not you, I was talking to
Four.
Miranda. I wasn't talking to you.
All right, so first thing is make sure you got the rows on the periodic table labeled. So 1, 2, 3, 4, 5, 6, 7. So from here, what we're going to do is I'm going to break these down each. Almost there. It's about to say.
Are we labeling these down here 6 and 7?
You can. So what I'm going to do, I'm going to break down each one of these at a time. We're going to break it down based off of the block. So remember, helium's not sitting in the P block. Helium sits here in the S block. So first thing we're going to break down is S block. When you look at S block, the rule for S block is N is equal to the rho. So the principal quantum number, N equals to the rho. From here, we get L, since we're in S block, L is what?
Something.
L is 0. Since L is 0, don't write this over this, okay? I'm just writing here because I can erase this.
Oh.
So don't write what I'm getting ready to write right here over D block. Since L is 0, that means M sub L is what? It's possibilities. Negative L to positive L, L is 0, so that means 0. So what that means is column 1 has a 0 orientation, column 2 has a 0 orientation. Oh, man. Out of
You
colors.
delete everything.
No, out of colors. I really don't want to use that, so I'll just put it. Then the last one we have is we have to break down the spin quantum number. So the spin quantum number splits the orientations in half. So it splits the block in half. So we have the first half is plus 1/2, and then we have the second half is negative 1/2. So the reason I'm showing this to you is there are, I need to text Kathy back. I'll leave it, I think it's funny.
What?
He just put his duck in front of the camera.
He's done it like 18 times.
I'm not editing it out. All right, so I want to show you what this is like and how this will work for you, okay? So I want to go through. So I need you to give me an element out of S block.
In a,
It's,
Allison. So here's what we can do. I can actually give you.
Pardon the interruption, but the following students are excused. Student council is going to do trunk or treat at Road Branch, and these students will be helping out. Kylie Lester, Jacob Mullins, Miranda Stewart, Miley Meadows, Jada Thornsberry, Kenzie Hatfield, Shade England, Rashaylin Bailey, Carson Painter, Reagan Klein.
So basically the entire class.
So what you're gonna do here is we start breaking this down, but here's the thing, it's not gonna matter for S and P block, but it matters when you get to D and F, so heed my warning. When you're doing these, you start with the angular momentum quantum number. Look at L first. L is based off the block we're in. I'm in S block, so what is L?
0.
0. This is why I look here first. You know how for D and F blocks, what we did the orbital notations, we said n equals the rho minus 1.
Yeah.
Well, now you can actually do this in reverse, and you actually need to find the rho. So for D block, n equals rho minus 1. So if I'm trying to find the rho will be equal to n plus 1. Look at L first. Now go to N. Since I know I'm in S block, I know N is equal to the rho. What rho is sodium in?
3.
So it's 3. M sub L, if you know how to break the periodic table down, then you know that that first column is the 0 orientation. So M sub L is 0. And then spin quantum number. Is it the first half or the second half?
It's the first half, so it's
So it's
positive.
plus 1/2. Did I expect you to walk out here knowing how to do this? No, I'm just trying to expose you to it, get you an idea of what's going on. Because you also can do the reverse of this. I can actually ask you for an element and give you 4 quantum numbers. So this one's different. start with L. So we're narrowing this down to find the element. So if I look at L is 0, which tells me what?
It's in the S block. Wait.
Oh, S block. Well, you can tell me anyway. Yeah.
She almost done.
So S block, since we're in S block, then we can now look, we've got it narrowed down to the block, now let's narrow it down to the row, go N. N is 4. Well, for S block, we knew that N is equal to the row, so that means the row is equal to N. So what row am I in?
4.
So I'm in the 4th row S block. I've narrowed this down now. It doesn't look like you've narrowed it down crazy a lot, but you actually have. So I've narrowed it down to these two. I've narrowed it down to potassium and to calcium. M sub L doesn't help us in S block, but it will in P, D, and F. So whenever you look at this, we're at the 0 orientation, so it really didn't narrow it down because both of these are 0, so we're still narrowed down to potassium and calcium. But look at the spin quantum number, -1/2. So it's -1/2, and the answer is calcium. Got S block? Let's look at P.
Oh.
Speaking of P. Now we're going to look at P block. Remember the P block, helium is not in the P block. So know the breakdown. Columns 13 through 18 is P block.
Hadley Evans is excused.
Are you gonna post that video?
Hunter Walls to the office.
It may not get posted tonight, but I am going to make it and post it eventually. So then what you're going to deal with here, looking at P block. If we look at P block, L is what? L is 1. So that means we're in P block, N is equal to the row. And then the big one is the orientation, M sub L. If L is 1, then M sub L can be -1, 0, 1. Here's where you have to remember the rules for how electrons act. Don't forget Hund's rule. Hund's rule tells us each orbital of an equal energy level will each receive 1 electron before it receives a second. So we jump. You run through the range, then repeat the range. So 13, -1, 14, 0, 15 is 1. Repeat the range, 16 is -1, 17, 0, 18 is 1. Then remember what happens with the spin quantum number. We spit.
I apologize for the interruption, but Kinley Sparks and Tinley Hicks are also released to go to Road Branch.
Alright, we get it, bro.
So we split the P block in half. So the left half is +1/2. The right half is -1/2. So choose me an element in P block.
Oxygen.
Oxygen it is. So we're going to get the 4 quantum numbers for oxygen now. We look at oxygen, we start with L, start with the block. Okay? Oxygen in P block, which means L is 1. since I know it's P block, I know the rule is N equals the row. So what do we get?
2.
We're in the second row, so N is 2. Orientation wise, this is where it's changed now. Break periodic table down, look above it, we labeled it out, what do we got?
Negative 1/2.
What?
Negative.
Not the spin,
Oh,
magnetic quantum number, sorry.
-1.
-1.
Where does the 1 come in for L? Like, why?
L tells me
The row.
the range for the columns, so I break the columns down. So how did I
It's
get
the
the
first
negative?
one in that. And that's when you broke it in half.
What do you mean?
Like it's the first one after the half.
Yeah, afterwards you break it down, yeah.
This is our special math for the next 2 weeks.
So spin quantum number, yeah. Spin quantum number.
Negative
So
1/2.
we're in the negative half because we're in the second half of the column.
What does where do you find the M and the L at? I don't know.
And so,
M sub L, that comes off of L. So where L is 1, the possible range is negative L to positive L, so it's -1, 0, 1. So that gives me the columns. Here's the thing. I don't expect you to be walking out here getting it today. It's just exposing to it. Like some people now, they're starting to kill it and starting to put 2 and 2 together.
No,
You're okay.
no, I'll give me a whole test on it right now.
Because like that, it's probably simple, and now it's like.
P block is where it becomes challenging. The reason I wanted to do P block is so I can get you thinking, oh, this isn't as simple as I initially thought. So that when we get to D and F tomorrow, it doesn't like